morning, Detroit. Welcome to Rapid NTCT. I'm very excited to be here. And as you just heard, it was a real challenge to get here. So let's get started. In the previous presentations here at Rapid NTCT and other places around the world, we talk about our technology. Today, we want to talk about the power of material jetting in the sense of what you can do with it. And I will present two applications from people here at the audience, two applications that seem small, but will have a huge impact, not only on additive manufacturing, but on our world in very different aspects of our life. So let's dive into the first one. A vicious killer, breast cancer. 500,000 people died only in the last year. Maybe there's a new direction to solve this challenge. MRI is very unique. There are certain tumors that you cannot find on mammographic or ultrasound, and even if you find them, you don't find the vicious ones. These tumors are detectable by the MRI, and the idea that AM will allow now is that once a suspicious tumor is found, this is the best time to freeze it and basically get rid of it. Ray Harter, I believe, is here. You will join us in the Q&A at the end. Developed as Marvel MedTech from Madison, Wisconsin, developed a sophisticated ceramic probe that can do this ablation process. What is needed to make this new device possible? There are a few things. Number one, since you use a probe or a device inside MRI, magnetic resonance imaging, you should have no interference with the magnetic resonance. Ceramic is ideal for that. You need a technology to create this probe that will allow you to make ultra-complex geometry, very tiny, small features, and it all has to come with a reasonable cost. Let's move to a whole different field. From healthcare to advanced antenna. Advanced antenna can be used on radar systems, on satellite communications, and recently, as you all know, in 5G wireless communication. The current solutions, current technologies that address this challenge are either very expensive by using a mechanical moving part or phased array technology. The idea or the need is to steer electromagnetic waves in a 360 degrees. You have a planetary transmission of electron beams, and you need to distribute it in any direction. You can do it with a matrix, a three-dimensional matrix of ceramic forms and voids that allow this vertical transmitted wave to be distributed to all directions without a single moving part and with a very little cost. Let's see what more it requires. Number one, it requires extremely accurate because it has very, very complex angle and features, and you have to be very accurate to steer this relatively very, very short electromagnetic waves to the right direction. You need a very smooth surface. Because if the surface, not only the external surface, but also the inner surface, where you have these tubes of ceramics, they have to be very smooth so we don't lose energy. You need a structure that can hold very, very small details, as little as 500 microns and sometimes even below. Also, it needs to hold structures that contain holes that are extremely small in diameter. The other challenge is that it has to be 100% density. Not only 100% density, but 100% density in a consistent, uniform way, even more than in the picture here, okay? And since 5G communication, each antenna covers a relatively short distance, I presume, less than half a mile or even close to a quarter of a mile. So in order to cover a city with 5G communication, with all the benefits that 5G brings, you will need thousands of antennas. The procedure, the process to make this antenna must be easy, it must be safe, it must be simple and affordable. In the next few slides, I will share some proof based on the video that you saw that support these needs. Material jetting is different. You saw the video. If it's not fully understood, you're welcome. We have many other videos either on our website or on our booth, 1103. Material jetting is different from anything that you see here or anywhere in the world in both the metal and the ceramic arena. Nobody, to the best of my knowledge, and please correct me if I'm wrong, nobody is jetting the material itself. If you look at most of the solution, and there are great solutions, great booths all over, I saw some this morning, they either jet a binder on a powder bed platform to create a layer, and then they do it over and over. So it's a great solution. Instead of jetting binder, a more legacy solution is to use energy source to bring it to the sintering point, either by electron beam or a laser beam. This is not the way we do. We jet the material in solid state by adding liquid that we create to create what we name ink, which is actually a suspension of the material that we want to put. Since we put the solid particles in extremely sub-micron size, we can use inkjet to do it, okay? And this is key to understand that this gives unique benefits. Let's see what they are. Number one, powder. Sometimes messy, sometimes hard to deal with, sometimes creating challenges. The powder is removed. There is no risk. No risk means less training, much high. I see a lot of faces that I know people already installed our machine. In this installation, in a couple of days, the operator could run the machine himself without any additional support and without any additional safety precautions. So we put the powder with the liquid in a bottle or a cartridge that looks like that, like a big Coca-Cola bottle, and you can put the ink, that's what we call that, into the system. Let's see what's the outcome of this approach. Accuracy. We are putting, as you heard, layered of few microns. so it's very accurate. The machine itself, the system is very accurate, and we use nanoparticles. This is a picture from the computer of the accuracy in millimeters. You can look around, you can hardly find any mistake bigger than 50 microns on the bottom left side. So from the exact planned part to the actual part that was printed, the distance is extremely small. The cube that you see, and it's a perfect cube, you may find it on our booth, it demonstrates that you could create very, very smooth surface from all sides and all axes. And this part was not polished or machined at the end. If we look at this microscope cross-section of this metal part, you can see there's no defects and no porosity. Same is achieved for, even higher than that, on ceramic. If you look at this cross-section, this is 15 by 15 by 15 millimeter ceramic cubes, enlarged, and you can see no porosity and very close to 100% density that allows the creation of the 5G antenna that I mentioned in the beginning. Now, systems are getting better and better. This is from what I found quoted on websites of different technologies. The highest, I took the highest of all the different providers. And again, you're welcome to make corrections if I missed something. But overall, all technologies reach up to a certain level. And the parts that you see on our booth today that were printed and sintered afterwards, 90 to 95% of all parts that you will see there were not machined afterwards. Okay, so they are as is. These are lab results, and this is supported by outstanding research on the use of nanoparticle jetting technology. And I would like to endorse the University of Youngstown and North Carolina. They will present here today in the afternoon. Is Eric here? Okay, he's not. But they show the results, and they open. This article that was just published shows that this ability allows now additive manufacturing to open a door to a much wider possibilities. Productivity is a main challenge. Our objective is additive manufacturing, no longer rapid prototyping. All our users, first users I should say, all of them are looking into real production of hundreds and sometimes thousands and sometimes even more parts. When it comes to manufacturing, it's not just the printing speed. Yes, we have a very, very high-speed process. We have thousands, 12,000 of nozzles jetting in 10 or 20 kilohertz. So it gets to 100 million or 200 million drops per second. But it's not only the printing speed. It's about the entire process. It's what you need to do before and after. Some people refer to it as the dirty little secret of additive manufacturing. When, also in a presentation by Gideon Levy a few weeks ago in Chicago, people showed that 70% of the total cost and time of the overall production, 70% of the overall, more or less, is by preparing the files, preparing the support structure, and making general preparation. But it's also eating up, gas filling, and a lot of powder vacuuming, if you're dealing with powder, removing support structures, and final polishing. The unique fact about material jetting, or nanoparticle jetting, as we branded our technology, is that we use two different materials. So you have the material, the build structure that you want to build, but as you can see, that's in this case stainless steel, but you also have a support structure that is made fully automatically by the system itself, by the software itself. So you basically need to do nothing. And the other thing is that the support structure is made of a material, and now that's the wow moment. For those of you who've never seen that, you're welcome to visit and see it. The big wow is that our R&D team managed to bring this support to be completely soluble. Maybe. This is the time, this is the key. This means that you remove big part of the post-process away. Okay? This means that not only that you print fast, but the overall process of manufacturing is faster, and this makes this solution relevant and cost-effective when it comes to printing hundreds and sometimes thousands of parts. A little bit on the business side, XJet, over the past 10 years, registered more than 80 patents to make this possible. It seems simple, but it requires a lot to put into the machine. It obviously requires what we call the best team in the world, at least in the inkjet world. We have more than 130 employees, and if there are people that are interested to join the team, we are hiring, so remember that. So we have the patents, we have the team, but that's not enough. In order to speed it up, we decided to build a state-of-the-art facility. You are very welcome to visit us. It's 7,000 miles away from here, but only 20 miles from Tel Aviv. And this is bigger, it's bigger than 10,000, bigger than this room, and it has 15 systems that are working day and night that allows us, since October, to test and to develop much faster new materials and to develop together with our users, some I mentioned earlier, new applications. To support the development for so long, we have invested more than $100 million already, and we are still very actively raising additional funds. This is news. Last year, I was presenting on this stage in, I think, Dallas, Fort Worth, and we had a single user here in the United States. By the end of this quarter, we'll have more than 5 installations here in North America, and globally, it's already in 2 digits in different applications. And if you come to the booth, you will be able, on the side, you will be able to see some of the applications being used, the variety of applications being used by a variety of customers from different industries, different geographies, that allow us to open the technology and to open new opportunities for additive manufacturing. A cost-effective additive manufacturing process with these new levels of accuracy, details, perfect density, and extremely simple operation open the door to endless application. But this is not the end of the story. I will give you a glimpse of what is happening today in the lab, things that will come to Rapid and to the market in the future. Being in Detroit, I couldn't resist to put this slide. I'm sure you're all familiar with this quote of Henry Ford. But if we look today on the show floor, including our booth, all technologies, all the powder bed technologies and even our technology today is using at some point a single material. It can be pure material, it can be an alloy, a metal alloy, but at a certain point of time, it's the same material. In most technologies, we believe that this will remain the case in the future as well. What you see now is a picture of the first parts that were printed with a printer. Our printer, this is the first time, it happened actually 5 weeks ago, that we managed to, after many years, we managed to have the eureka moment of being able to combine not only 2 different colors or not only 2 different metals. We managed to combine You're very fortunate because this was the first time we succeeded. It's still unsintered. I have the sintered part as well. But this is the first time that, to our best knowledge, anybody in the world managed to print ceramic and metal. The ceramic here in the center, that's the white one, is zirconia, and the metal is stainless steel 316L. Together, combined, since this was printed, I keep the original. We printed many more, and we still have a long way ahead of us. The head of R&D, Igal, you can raise your hand. A lot of work on this guy's shoulder, but this is a revolution because it opens a way to a very broad potential that we are not sure yet where it can go, and I welcome you to come to our booth at the end of this presentation or at any time in the last 2 days of the show and talk to us because we want to partner with you. We wouldn't be here today telling you about these beautiful applications and some others that I'm not allowed to speak about without your help. So your work and your ideas are essential to our success. Thank you very much.
Thanks, Dror. That was terrific. I have about 5 minutes for questions. Who has questions? Anybody want to get started?
Dave, just before we get started, we have Ray from Marvel MedTech here.
I chatted with Ray at the party last night. This was fascinating stuff.
So if you want to learn more about the medical application that I explained, that was the first one, you're welcome to direct the question to Ray. Also, we have Mark here from raise your hand, from the University of Delaware, came with this fantastic, unprecedented solution to make 5G antenna in a cost that is, how much?
Questions?
Will make it 10 times cheaper to implement than the current solution.
Come on, somebody's got to have questions. Here we go. The guy furthest away from me has the questions.
Thank you. Great presentation and fascinating technology. How thin a feature can you actually print?
The question is how thin the feature. Obviously, it depends on the aspect ratio. We printed, the lowest was 0.1 millimeter. And there's a part on the back of our booth that's called the drill. Everybody is welcome to check it out. It's made of zirconia. We are now also printing it in stainless steel. We'll show it in the next show. You see holes that are 190 microns in diameter, 2,000 connected channels, 2,300 connected channels of 190 microns. Does this answer your question? Thank you.
Right here, Dror.
Yeah, hi. I just want to know what are the material strength look like after printing?
Okay, the strength, the part, I don't know if it was clear enough in the movie, not all of you were there. The part comes as a green part, but it's already, because there's so much less binder, it's already better than metal injection molding, for example, or ceramic injection molding. After sintering, And this is a big claim. After sintering, the mechanical properties that are now being tested by our own users are identical or almost identical to the mechanical properties of the real material. So what we see as a challenge is to reach general ceramic or general metal mechanical properties in terms of any parameter from flexural strength all the way to elongation to break, conductivity, thermal conductivity, heat conductivity, electrical conductivity, and so on and so forth. So the results are identical. The other thing is that they're very isotropic. Because we create a green part and only then put it in the furnace for a few hours, we do not see, and this has been tested recently in different parts of the world by our own users, there's no difference in the shrinkage factor or in any mechanical properties between the X, Y, and the Z, which is also quite unique for additive manufacturing. Thank you.
Yeah, you asked for some corrections. Thank you very much for your very, very good talk. You mentioned here it is.
Too much later.
You mentioned the density of different AM technologies, and you said for laser powder bed fusion, 98 to 99% would be the density. It's easier to reach 99.9% with respect to 98%. So the total of all parts that these technologies produce is normally 99.9% dense.
Thank you very much for this comment. Thank you very much. There's one there.
One more question.
Can you do the multi-layer printing?
Say it again.
Can you do a multi-layer printing? You know,
Multi-layer.
yeah, multi-layer.
Multi-layer?
Multi-layer.
Yeah, I mean, on a build platform, let's say you do 100 parts in one layer.
Yes.
And then on the
Yes,
stack,
absolutely.
can you stack it? And
Yes.
how high it can go?
This can make sense if this is additive manufacturing technology. So on one hand, a lot of our users now are using it for making the same parts many times. If all the parts are of the same altitude, you can then put another layer and another layer, as many as you want. Actually, the support structure, since it's solvable, will take care of that. So this is a very good question. We have a customer in Europe that makes on one tray 430 parts in one shift, and he considers now and is making some attempts to double that. Okay. But at the same time, from productivity perspective, sometimes it's best to take the tray, put it in water, basically water, remove the support, and then put it in the furnace for final sintering. At the time that you took it out, you can put the next layer. But if you ask from technical perspective, yes, that's very doable to put one layer and then another layer and as many layers as you.
Ask one more question. Sure. Can you give some indication on the cost of the material? You know, the material that comes in the canister.
Yeah, the cost of the material is very competitive. I mean that it took us a long time to drop the cost, and we were still working on that. But basically, the way it is presented today is that it's very competitive in comparison to alternative AM technologies. It's not competitive to general.
Okay, everybody, let's hear it for Dror Danai, the CBO of XJet on the power of material jetting. That was a terrific presentation.